In FTD, if a cell serves a large number of online users, the CQI adjustment period is prolonged and the CQI adjustment algorithm may receive multiple HARQ feedback messages in a CQI adjustment period. The Downlink CQI adjustment delta optimization switch option of the CQI adjustment algo switch parameter specifies how to calculate the CQI adjustment value. When this option is deselected, the CQI adjustment algorithm treats all the received HARQ feedback messages in a CQI adjustment period as a single feedback message, based on which the CQI adjustment value is calculated. When this option is selected, the CQI adjustment algorithm calculates the CQI adjustment value based on each individual HARQ feedback message received in a CQI adjustment period. This calculation method causes fast CQI adjustment. The I-layer convergence performance improves and downlink throughput increases. CQI is a value that indicates an estimation of the modulation and coding scheme, MCS, that the UE can receive reliably from eNodeB. It reflects the SINR on different physical resource blocks. Due to the time spent on transmitting and processing signals, a delay between the CQI report and its application in eNodeB is inevitable. As the channel condition changes constantly over time, the mismatched CQI could consequently result in a reduction of the data throughput and the performance degradation caused by CQI delay. To improve the quality of service, the CQI prediction schemes for LTE is performed using the CQI filtering adjustment feature. The eNodeB applies filtering to the reported CQIs. The initial filtered value of the CQIs reported by a newly admitted UE is determined by the reported CQI filtering initial switch option of the CQI adjustment algo switch parameter. This function does not take effect for UEs running services with QCI1. If this option is selected, the initial filtered value of the reported CQI is determined based on the CQI value reported by the UE, and the filtering coefficient for the reported CQI in the first several reporting periods is adjusted. If this option is deselected, the initial filtered value is always 4. The CQI filtering can be adjusted based on the spectral efficiency. This function can be used in low-speed cells with 4 CRS ports. In FTD, it takes effect for UEs in transmission mode 4. In TDD, it takes effect for UEs in transmission mode 4, or transmission mode 9. This function is controlled by the CQI filtering spectral efficiency optimization of the CQI adjustment algo switch parameter. If this option is deselected, each time the eNodeB receives a CQI value from a UE, it directly applies filtering to the reported CQI, and the previous filtered CQI. If this option is selected, each time the eNodeB receives a CQI value from a UE, it determines the difference between the reported CQI and the previous filtered CQI. If the difference is large, the eNodeB adjusts the reported CQI based on spectral efficiency optimization, and then applies filtering to the adjusted CQI and the previous filtered CQI. If the difference is small, the eNodeB directly applies filtering to the reported CQI and the previous filtered CQI. An eNodeB calculates a CQI adjustment value for a UE based on HARQ feedback. It sets an initial value for the UE during initial access, RRC connection reestablishment, or incoming handovers. The larger the CQI adjustment value, the more aggressive the MCS for the UE. The smaller the CQI adjustment value, the more conservative the MCS for the UE. In FTD, the initial CQI adjustment value for UEs during initial access, RRC connection reestablishment, or incoming handovers is specified by the initial delta CQI option of the CQI adjustment algo switch parameter. When the initial delta CQI parameter is set to a large value, the initial MCS index for a UE is high, which may lead to a high block error rate. If this parameter is set to a small value, the initial MCS index for a UE is low. When the initial delta CQI parameter is set to a value smaller than -1, and the UE reports consecutive positive ACK, as feedback on downlink HARQ. The downlink throughput can be improved by enabling the precise MCS adaptation switch option of the CQI adjustment algo switch parameter. The eNodeB adjusts the reported CQI value for the UE, and increase the transport block size index used for the first downlink HARQ retransmission. The increased amount is specified by the downlink first HARQ transmission transport block size index number option of the cell downlink scheduling algo parameter. The precise MCS adaptation switch will allow the eNodeB to increase the transport block size index in a conservative initial delta CQI value. The CQI adjustment algorithm adjusts the reported value in steps to maintain the coherence between the reported CQI and the RF channel quality changes. The adjustment step can be a fixed value, variable, or adaptively variable. The eNodeB can fix the CQI adjustment step to the CQI adjustment step parameter. For UEs during initial access or incoming handovers, the CQI step can be fixed to the CQI adjustment initial step option of cell downlink scheduling algo parameter. Variable step-based CQI adjustment. This function is controlled by the step vary switch option of the CQI adjustment algo switch parameter. If this option is selected, the eNodeB determines the CQI adjustment step based on the UE opportunity to be scheduled in the downlink within the next 100 milliseconds. If the UE is less than 10% likely to be scheduled, this means that the UE is not accessing many downlink services. The CQI adjustment step is adjusted based on how the IBLIR is far or divergent from the configured target. The farther the IBLIR is from the target, the larger the adjustment step, which helps the IBLIR more rapidly approach the target. If the UE is at least 10% likely to be scheduled, this means that the UE is accessing many downlink services. The CQI adjustment step is fixed to the value of the CQI adjustment step parameter. Adaptive step-based CQI adjustment. This function takes effect when the adaptive step vary switch parameter is selected, and the CQI adjustment step parameter value is used as the CQI adjustment step. If this option is selected, the eNodeB adjusts the CQI adjustment step based on the HARQ feedback for downlink transmissions. If the eNodeB consistently receives HARQ ACKs for downlink transmissions, it increases the CQI by a large step. If the eNodeB consistently receives HARQ NACs for downlink transmissions, it decreases the CQI by a large step. To monitor the CQI optimization features, the following slides show the KPIs and counters that will show the impact in terms of throughput, traffic and channel quality. The average CQI, as described above, provide the average value of the reported CQI by cell, or eNodeB level. The average MCS index, provide the average MCS value used for the downlink scheduling. The counters measure the number of times that an MCS index is used for scheduling in the downlink, and the MCS index ranges from 0 to 31. MCS index 29, 30, or 31 corresponds to a modulation mode for retransmission. The PDSCH IBLIR rate, provide the rate of the initial downlink erroneous transport block size index. The counters measure the numbers of downlink erroneous transport block size index after initial transmission in QPSK, 16 QAM, 64 QAM, and 256 QAM modulation schemes. The corresponding counter is incremented by 1 based on the modulation schemes each time the eNodeB receives a transmission failure indication of an initially transmitted downlink transport block, each time the eNodeB receives a NAC as HARQ feedback. The PDSCH residual block error rate, provide the rate of the erroneous transport block size after the max number of retransmission is reached. The counter measure the number of downlink erroneous transport block size after the maximum numbers of retransmissions in QPSK, 16 QAM, 64 QAM, or 256 QAM modulation scheme is reached. incremented each time the eNodeB receives a transmission failure indication of a downlink transport block even when the number of retransmissions reaches the maximum value. The PDSCH residual block error rate should not exceed 2%. The user downlink throughput reflect the impact of CQI optimization, which can be increased in a stable traffic volume, or can be decreased if the CQI optimization brought more traffic volume. The cell downlink average throughput KPI is calculated based on all the data transferred at the downlink and the time it takes to transfer. The CQI optimization will show an increase in the cell downlink throughput. The downlink traffic volume can be increased depending on the cell traffic model and the number of users in the cell. The downlink packet loss rate KPI indicates the downlink packet loss situation of a cell at the PDCP layer. This KPI is calculated based on the number of dropped PDCP-SDU and the total number of downlink PDCP-SDU transmitted for services carried on DRB with all QCI.